So one of the things that everyone, including myself, want to know more about are black holes. Just some crazy physics associated with, I think, a phenomenon that we call black holes. They call a black hole black because if there are photons that want to escape the gravitational influence of a black hole, even going the speed of light, which is how fast photons go, they aren't going fast enough to escape the gravitational pull of that object called a black hole. So we've talked about black holes being formed at the end of a star's life after a supernova type 2 event. These are called stellar black holes, and we're actually going to talk about other types of black holes, but what they have in common is that not even light can escape their surface. So just to kind of emphasize this, we could have an object with a given mass and squish it down more and more and more and more, maybe much like if you have, I've mentioned recently, one single trash bag at Christmas time, and you have to get all of the trash in it. So you take this, in that case, you keep adding mass to it and making it and squishing it down. But if we take an object with the same mass and squish it down farther and farther and farther, notice that what will happen is, in order to escape the gravitational influence of that object, you have to go faster and faster. Your escape velocity increases. So there's a short video out there by Bill Plate that is with Bad Astronomy, and I put it as part of my playlist. He does such a great job of talking about the gravity associated with a black hole. And actually this little applet, if I were to open it up, would show us that if we take an object and, again, let it have the same mass and squish that object down, we can take any object, such as the Earth, and make a black hole out of it. Now, what we'd have to do with the Earth is go ahead and take its diameter, its radius of about 6,000 kilometers, and shrink that down to less than 1 centimeter. And then what we would have is an object we call a black hole. So some features, or an important feature of a black hole, is what we call its event horizon. And now its event horizon is actually kind of the region in space around the black hole is beyond which nothing can escape, because the escape velocity is in excess of or at the speed of light. And the speed of light, as it turns out, objects cannot go any faster than the speed of light. That's Mother's speed limit. I love that phrase. So another feature of a black hole then is something we call the Schwarzschild radius. And the Schwarzschild radius is from the center, is from where the black hole is, out to the edge of the event horizon. So it's that radius. So the size of a black hole in general, if we first off, I guess, start with a neutron star, we said that an object needs to be at least 1.4 solar masses, that stellar corpse, and you can get a neutron star out of that after a supernova type 2 event. If it is 3 solar masses or greater, then that object that's left after a supernova type 2 event will give us a black hole. And here's kind of relative sizes of a neutron star and a black hole. Poor Lansing, superimposed over Lansing. And this animation would simply show you, this is my tickler to remind you, that the more mass a black hole has, then the larger its radius, the larger that what we call Schwarzschild radius, out from the center of the black hole out to the event horizon. So on this figure, that dot, 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 that's the event horizon, and that green thing in there is the black hole. So as we make the black hole more and more massive, that event horizon swells. So Einstein, among other things, has what we call his general theory of relativity. And in it, he describes something called space-time, the fabric of space-time. I love this concept, the fabric of space-time. I generally kind of think of a sheet, like a bed sheet, kind of pulled out straight. And so actually what Einstein said is that space and time are interrelated. And so that as objects rest on the fabric of space-time, they make sort of kind of dents, just like if you were to hold a bed sheet taut and put dents on, or excuse me, put objects on it, they would make these dents. And so you might imagine then we can make the objects heavier, more massive, and actually density then would play a part in the relative how compact the object was. But we think of space-time like this, and so I really like when we talk about the Big Bang, the unfolding of our universe, kind of the unrolling of this fabric of space-time, and how space-time is actually continuing to expand. I just think that is so cool. Well, what that has to do with black holes is this. So if we think of the fabric of space-time kind of stretched out here, then we put an object. This could be maybe a neutron star, pretty darn dense. Density has the density of an object, how squished together that matter is, then has an influence on what sort of dent it makes in the fabric of space-time. Well, a black hole actually makes such a strong dent in the fabric of space-time. We can kind of think of it looking like this, where it looks like there's a hole in the fabric of space-time. And this is my little note to self here, that if you're using Mastering Astronomy, that goes along with this text. They have a great applet out there that allows you to excuse me, play around with different objects in the fabric of space-time. So what's important about all black holes? Now, we've talked about black holes that come from the end of a massive star living its life and going out supernova type 2. And we said you get a black hole if that stellar remnant, that core, is more than 3 solar masses. It will actually be compact enough to make this object we call a black hole. But this is what we call a stellar black hole, and there are other types of black holes we'll be talking about soon. So what all black holes have in common is that an object going the speed of light cannot escape its gravitational influence. So, well, what happens to that material? Well, the gravity will pull. If you have an object that's in the vicinity of a black hole, and if it's within what we call the event horizon, then that object or that material will fall into the black hole and become part of the black hole. And this just kind of blows my mind. We talked about, maybe one way to think of it is we talked about when neutron stars form, we said that protons and electrons combine to form neutrons. Well, and that's related to the pressure, the vicinity that those protons and electrons are forced to be in. Well, with a black hole, even something even more exotic happens with the matter that falls into it. It becomes part of the black hole, and it kind of loses its general identity. Oof. So singularity actually is that point of what we call infinite density. That's the black hole itself, is the way I think of it. So singularity is the black hole. It's the material of the black hole that has fallen into an infinitely dense object. So here's the deal, and again, I refer back to Phil Plait with Bad Astronomy, who does a good job at kind of summarizing this. If you take an object the size of the sun, for instance, if you take the sun and you shrink it down, you get a neutron star, you take that sun and you compact it down even further, and you get an object we call a black hole. Well, if the Earth will keep orbiting, everything in our solar system will just continue to do what it was doing before our sun turned into a black hole. Black holes do not seek objects to suck, to become part of themselves. Okay, black holes are simply another object out there resting on what we call the fabric of space-time, making a dent. And so it will influence the trajectory of objects. But especially as they come close enough to the event horizon or within the event horizon, objects are not going to be able